So we've been talking about Newton's law of motion, how force equals mass times acceleration. And I know I've gone over a couple times, how if one thing like mass goes up, then force goes up, or if acceleration goes up, then force goes up. But I want to hone in to make sure that I have emphasized enough exactly what this equation means. And what it means is that if you want to take an object that has a mass and accelerate it, say from rest, put it in motion, the force you need to do that is equal to only two things: mass times acceleration. Now, again, it also depends on friction to some degree, but we're not talking about friction here, right? We agreed that because friction, when you add it in, it makes it more complicated. We wanted to keep this easy right now. And what the scientists do is when they calculate, they get close to the answer, by using an ideal formula like this, the ideal. And then if there's things that affect that, they can add them in at the end to get a more exact answer if they need one. So we're leaving friction out right now, which means only two things affect the amount of force you need: mass times acceleration. Now, if you have two objects and one of them is heavier than the other one, more massive, then it's going to take more force to get it going. And that should make sense to you if you think about it. A more massive object like a truck is harder to push to get it going than a little toy truck. So the bigger and more massive and heavier it is, the harder it is to get it going. Weight or mass. Or if you have two objects the same, and they're the same, but you want one to go faster than the other one, you have to apply more force. And that should make sense to you too if you think about it. It takes more work to get it to go faster than to go slower. So this formula should really make sense. And it's so elegant because it's so simple. You think about physics formulas are complicated. Nature isn't always that complicated. Sometimes it's very simple. And then we talked about gravity when you drop an object and how gravity is acceleration. So since gravity is acceleration, we can take and we can put G for gravity in the equation and say mass times gravity, because gravity is an acceleration. And that force, we called it weight. How heavy you are depends on your mass times the gravity where you're standing. Remember, from there, we talked about how gravity applies to the whole universe and how things orbit each other based on gravity. They're falling by gravity, but they're falling, if they're going the right speed, then they're falling at the same rate the Earth or whatever star or whatever is curving away from them. So that is where I wanted to start out. I ran into a neat little quote in a paper that I was reading, Science News, called Einstein's Genius Changed Science's Perception of Gravity, because this is what we want to talk about when you get to the models, is his Newton's and then Einstein's model of gravity. And it says that Newton's law of gravity had united the earthly physics of falling apples with the cosmic dances of planets and stars. He united falling apple with, how the stars and everything in the sky move. And so I thought that was kind of a neat little quote. Now, today, we want to get back and talk about models again. And like I said, I want to talk about gravity. And on that, we have another little formula. And again, you don't need to memorize this. What I'm trying to get you to do is to see how to work with equations and how formulas using letters can explain things, how things work. And so this was Newton's model of gravity. If you have two objects, like say one of them's the Earth and one of them's you, or one of them's the Earth and one's the moon, or just two different balls hanging from strings like they show here. Okay? That the only thing, the force of gravity pulling them together, of one is the same as the force of the other, and those is equal to this very simple formula. The mass of the first one times the mass of the second one divided by the distance between them. That's R for radius. I would use D for distance, but that's all right. The formula uses R. But we talked about proportional, where if one mass goes up, that means the force goes up. The heavier this is, the more force there is between them. But it's inversely proportional to the distance. But it's inversely proportional to the square of the distance. And that means, remember, square means R times R. So if R is 1 foot, R times R is 1, then the force is just equal to the mass times this little thing here we'll talk about in a minute, what this is. Okay, but if it's 2, then it's not 1/2. The force isn't 1/2. If they're twice as far apart, the force isn't 1/2. It's 2 times 2 is 4, or 1/4. So you see, when it doubles the distance, it's 1/4 the power. It gets weaker and weaker and weaker the further away you get from it. So what is this little thing here? Well, when we go back to the equation we had of force equal mass times acceleration, I should have written it down, but remember, mass is in kilograms. And acceleration is in meters per second squared. And we decided that kilogram meters per second squared, I could just draw that whole line over there because it's just kilograms times meters, or kilogram meters per second squared. We decided is going to be equal to 1 Newton. And we made up the name Newton, and we said this Newton is equal, 1 Newton equals 1 kilogram meter per second squared. So since Newton was a new thing and we just made it up, we didn't have to worry about what I'm going to talk about here on this other one. In this case, you have mass times mass, or kilograms times kilograms, and distance times distance, or meters times meters. So you have kilogram per meter squared, or kilogram squared per meter squared. But we know that force is in newtons. So we the units don't match. And I know your teachers have, and I've mentioned units are really important. And a lot of times people don't get used to checking their units, but you really need to. And so here you have kilogram meters per second squared. And here you have meter squared, kilogram squared per meter squared. Two different units. So how do we get them to match up? Well, you multiply them by this, we call this a constant because it doesn't change. I'll mention that again in a second. But basically, doing your math, and you don't need to memorize this, just make sure you understand what I'm doing. But basically, if you take, you want to get G by itself. So you multiply by r squared. So it goes F1 times r squared. And I can't draw a little square up there. I have to use a shortcut to mean squared. But you have F times r squared. And then you divide by m times m, m1 and m2. So G equals that. And that, remember, that force is measured in newtons. Distance is measured in meters, so you have Newton meters squared. And mass, both of them, are measured in kilograms, so you have kilogram times kilogram. So you have Newton meters squared over kilogram squared. So that's what G equals. So we have Newton meters squared per kilogram squared. Okay. But this number also has to be multiplied by a number, not just the units. The units are right, but we also have to multiply it by some number. And I guess what I'm trying to get at here is before we made up a new unit called newtons, so we could equal 1 newton to 1 kilogram meter per second squared. We can't do that now because we already have newtons for force, and we have this over here that's in a different unit. So they don't, we can't make up and say, okay, one of these equals one of these. So therefore, that's why we have to adjust the units and also multiply by a particular number called a conversion factor to convert. Just to help you understand that, it's basically the same thing when you say there are 2 pints in a quart. If you want to convert pints to quart, you have to multiply the number of pints, or divide them actually, by half to get the number of quarts. Or the number of cups in a gallon, you have to multiply the gallon, 1 gallon, by however many cups there is in a gallon. You convert it. And that's what we're doing here, is we're converting. And remember when we talked about variables, we said sometimes a letter stands for, it changes all the time. Well, mass 1 and mass 2 is going to change depending on what mass you're using in your experiment. You're going to do 1,000 experiments, and you might do them with all different size masses just to make sure that it always comes out according to your formula. So those are always going to change. You also change the distance apart in your experiments, so that's going to change. This is a constant. It equals this all the time. Now, that doesn't mean you can't use the letter G to stand for something else when you're talking about something else. But when we're talking about Newton's law of gravity, G is a constant and is always equal to this number. So the only thing that makes this a little more tricky is you have to multiply the 2 masses and divide by the square of the distance, and then you have to convert that using this number to get how many newtons of force. And this, we've been talking in metric, but the same thing applies in the English system to get pounds. Now, when I first remembered a long time ago seeing a picture how Newton did this, he took a little ball and a big ball, and then he doubled it just to balance the weights, and also twice, because gravity is so weak. By doing it with two of them, it makes it a little stronger, and then you divide your answer by two. So, just the two size balls would be here, and then as this small ball gets attracted to the big ball, it would twist this, turn it. Now, they've got a mirror here. The ones I saw, but I couldn't find a picture of them, were just like a long arm coming out here to a ruler, because a teeny tiny little move in here would make a bigger move out here. And they use a mirror instead, and it does the same thing, because they shoot a light, and a teeny tiny change in the mirror move, and you send the light wave way out here, that makes a bigger move, and it's easier to measure. So that's basically how Newton did it back in his days to figure out, this formula. Now, here's another picture of another thing they use. Cavendish used this one. This is a sketch from one of his notebooks, another scientist. And I don't totally understand, but I think what's happening is these are springs here. So I think when they roll these balls out into place, right, in between these two, and that adds the gravity. And so now they're attracted to each other. And I think that tips this back and forth. Which also moves this up and down. And they'd put a ruler here and they would measure it there. The attraction, between the two, how much it moved them. So that worked for hundreds of years. But it wasn't perfect. There were a couple problems with that model, and they couldn't figure them out for hundreds of years until Einstein come along. So remember how we talked about it needs to be a good visualization, it needs to explain, and it needs to predict. Well, there's a couple things that model couldn't explain. So sometimes when you learn new stuff, you get a better model. Doesn't mean the old one is wrong. It just means now you have more information and you get a better one that explains it better. And that's what Einstein did. And so that's what we're going to talk about in the next lesson. So there was a problem with Einstein's model that they never could figure out. Now, there was actually a couple things. One of them had to do with the orbit of the planet Mercury. And I don't know the details on that. We're not even going to talk about that. But the biggest thing is that his model implied that as soon as you put this mass up next to this mass, gravity pulls them together. Now, the problem is, how does something way over here affect something way over here? Now, everything we've known up until now has used waves. Like, for instance, you have sound waves.
When an object vibrates, it pushes the surrounding air molecules into one another, starting a chain reaction of collisions through the air. These collisions travel in waves. When they strike your eardrum, it vibrates. This vibration is converted into electrical signals that your brain recognizes as sound.
Okay? Now, even if there is no air molecules, like out in the middle of space, we send radio waves. A moving magnetic field creates a current in a wire, or how a changing current in a wire creates a magnetic field. Well, this fellow named Maxwell came up with some equations that describe those, and they're pretty darn complicated. We're not going to get into those, believe me. But basically, this is a model of that, where the red is the electric field and the blue is a magnetic, and the electric field, when it dies off, creates a magnetic, and the magnetic field creates the electric. And he predicted, long before they ever could do it, just using his math, he predicted that these waves should be able to be sent to space. And it was after he died, actually, that they found that they could do it. And that's how you have radio and television and Wi-Fi and all this stuff today. He predicted it just from his math equations that you should be able to do it. There's an example of how a model can predict something. But you see, both of those things used waves. And waves, the electromagnetic wave, for instance, travels at the speed of light. And this same fellow, Maxwell, proved that nothing can go faster than the speed of light. So, unless there's waves between, say, the sun and the earth that's causing the gravity, and they hadn't discovered waves yet, and his formula didn't allow for anything. His formula showed it should be instantaneous, not at the speed of light. Now, of course, back then, they couldn't measure the speed of light. Their instruments weren't sensitive enough. They, had hourglasses for time. But anyway, Einstein figured out a better model. And so this is an example of how models improve when they figure out, or, when there's things that the old one don't explain, or they figure out new information. Now, Einstein, this doesn't have anything to do with that. This is just to show you some of the weird stuff he come up with that they proved was true. But he had one theory called special relativity. Then he had another one called general relativity, and the general had to do with the gravity that we're talking about. But the special he come out with first explained something a little different. And this just to show you how weird science can be. So just, hope maybe this will get you a little bit interested in it. It does me, because this stuff's really interesting to me. But if you were standing down here watching a train, and there's a person riding on the train, and that person throws a ball. If the train is moving at 10 meters per second, I don't know what they put that little X in there. I should have erased it before I pasted this on here, but I didn't. So never mind the little X. It's moving at 10 meters per second. And he throws a ball at 5 meters per second. When you're on the ground, you're going to see the ball moving away from him at 5 meters per second, plus the train's moving at 10. So the ball is going to be going 5 plus 10, or 15 meters per second. Now, we just got done saying that speed of light, and that's what this little c, usually we use that to stand for the speed of light, 3 times 10 to the 8th meters per second. But it's a way of writing a huge number really small. It means a 10 followed by 8 zeros. And so you see we have 8 zeros over here. So 3 times 10 to the 8 is really 300 million meters per second. And just to give you an idea, that's almost a billion feet per second, which is also close to 185,000 miles per second. Now, if you're going 100 miles per hour, and there's 3,600 seconds in an hour, that would mean you'd be going 1/36th of a mile per second. It would take you 36 seconds to go a mile. So you're going 1/36th of a mile every second. Compare that to 186,000 miles per second. Quite a big difference. So the question becomes, if nothing can go faster than the speed of light, supposing this train was traveling at almost, say 9/10, 98.98, whatever, pretty close to the speed of light. And instead of a ball, he turned on a flashlight. Using our normal math, if this was going the speed of light, he'd be going 300 million meters per second. If he turned on the flashlight, that flashlight light would be going 300 plus 300, 600 million meters per second. That's how fast that light would be going when you're watching it. But that can't happen because nothing travels faster than 300 million meters per second. So if he's going that fast and he turns on a flashlight, what happens? If the light can't go any faster than what the train's going, does the light come back and hit him in the face? Does the light come back and smack him in the face? No, it doesn't. And Einstein figured that out, but you know how he did it? Get ready for this. When you're observing somebody from the distance and you're measuring time, time is different from what he's measuring. Time stretches out. So when you're going the speed of light, time stretches out. Also, distances get shorter. So what you're seeing that you think is going 600 million meters per second isn't really going that fast, because when he's traveling near the speed of light, time stretches out and distances are shorter. Now, if that doesn't blow your mind, that is some weird stuff there. And there's all kinds of neat things that one of these days we could talk about when it comes to that. Like if you're sitting on a barn and somebody's coming at you with a 10-foot pole and your barn is 10 foot. No, he's coming at you with a 20-foot pole and you got a 10-foot barn. Since he is going at the speed of light towards you, that pole is only half as long. So he thinks it's 20 foot. You think it's 10 foot. Can you trap that pole just for a split second in that barn by closing the front door, then opening the back and letting them out? Just for a split second, catch that 20-foot pole inside your 10-foot barn because he's going to the speed of light. We're not going to get into the answer to that. I just want to try to pique your interest in some of the things. Once you learn the basics, there's a lot of neat stuff out there. So enough about that. The point is, this Einstein figured out some pretty weird stuff. So another thing that's pretty weird was his model for gravity. Now, I tell you what, I'm sitting here. If I want to try to bend space, you think we could do it? Even if we have air molecules in there, we still can't bend it. Out in outer space where there's no air molecules, how are you going to bend it? But he hypothesized, and they've proven this many, many times that it seems to be accurate, that a huge mass, what it does is it bends space, bends it. And there's another little bend here for this one, smaller because it's smaller. Let me move my picture up out of the way. So I had a video of this, and I can't find it, so I just got a photo. But what happens is, you see, is something it can circle around because of this bent space, and this model then explains the same thing that Newton's model did. So he didn't change it, he didn't say it's wrong, but Newton couldn't explain how it worked, since it seemed to be instantaneous. But how could it be instantaneous, and how could something over there affect over here? And there were no waves at that point anyway, and if there were waves, they couldn't travel more than the speed of light, and that means it wouldn't be instantaneous. So this explains the same thing that his model does, how things orbit. Due to it being curved, it can rotate and orbit just the same as Newton's model. So it explains the same thing, but this model, again, I don't know the details, but this new model explains Mercury, the oddity about its orbit that Newton couldn't explain. I guess what I want to say is, number one, this fits your definition of a model because it's a good visualization. You can picture it in your mind. It's good because it explains how gravity works, and the Newton model couldn't. Even though it's weird thinking about bending space, but the model does explain it. And there have been, over the 100 years since he first proposed this model, over 100 years, they've tested it thousands of ways and haven't found any problems with it yet. So in terms of predictions, one of the things that it predicted is, if you look at that, light's traveling along here. Okay. Light's traveling along and it hits that spot, it would bend. Well, we didn't think light would bend. So they set out and did some experiments, and they found at a certain exact time when something, moon or something, was over here where you couldn't see it, because here from the Earth is a straight line, and this is where you would see, and it was over there, so you couldn't see it. And sure enough, the light bent around the sun because the gravity of the sun, the light bent, and you could see it. They didn't think they'd be able to, but they could. And Einstein's theory predicted that, and it turned out to be true. So a couple other things it predicted was that the universe is expanding. Well, back in those days, they didn't think it was true. Matter of fact, Einstein was fooled. He didn't think it was expanding, and his formula said it should. So he added what they call the cosmological constant to his formula so that his math would come out that it wasn't expanding. Years later, the Hubble satellite that's out there taking pictures of outer space, I don't know where it is now, on its way out toward Pluto somewhere by now. But we got a lot of good pictures of space as it traveled out through the galaxy. And Hubble proved, the information we got from Hubble proved that the universe is expanding. So his equations were right to begin with. He just didn't believe me. He was a doubter. Um, so the expansion of the universe is one thing that was predicted that turned out to be true. The other thing that was predicted, and this is pretty neat, black holes. If you've ever heard of black holes, the, I don't know exactly what they are, but they're so massive. They've got so much gravity, so much matter packed into them, that their gravity is so strong that they just suck everything into them, including light. And because light is sucked into them, they're black, because the light can't escape. Well, here's a picture of two black holes colliding with each other. Uh, okay. So, with that much gravity spinning around as you saw it, when you look at that uh, with a little diagram here of Einstein's, they call it space time, you see how things can distort. And you see how it tugs. You see how it's tugging on. When it pops up there, it's pulling, way out here. So the thing of it is, if our planet, the Earth, is out here somewhere, and those two black holes are causing all those gravity waves, it seems like if there are waves, they weren't sure there were yet. They have found that it does those distortions. I guess this is sort of like a net out of string, where when you tug here, then that pulls in, and then that pulls in, and then that, and it takes time. And so it does travel at the speed of light, is what they found. So there are waves. We just didn't have instruments that were sensitive enough to measure it. So what they did is they set up an experiment so that they could watch when these black holes collide. And here's a picture of LIGO. What they did is, this building has two arms, one that goes out that way and one that goes out another way. And that way, when gravity is pulling back and forth on this one, it gets shorter and longer. And if it's pulling this way, that one gets shorter and longer. And what they do is they shoot light down here and have mirror at the end, and the mirror bounces the light back. And so they have it in two directions, so that if the light is pulling one, and it's a tiny bit shorter than this one is, they can measure, the difference, because when there's no gravity pulling, they're both going to hit the same time. But when there's gravity pulling, they can measure the difference in time. And they've been able to do that. So they've actually been able to measure gravity waves now. And so that was all predicted by this model. That's what a good model does. It's easy to visualize. It explains everything. And you can make predictions with it.